This is section 525. We're going to take a look at complex zeros. So we're going to understand how complex roots exist in a polynomial and write a polynomial using complex roots. Now let's look at these three different scenarios. Now we can solve this statement here, and if you solve it, you're going to get zeros, 0 and 4. We have two real solutions. For this one right here, if I set that equal to 0, you're going to get x equals 2. We only have one real solution. But in this third scenario here, if you were to go to try and solve it, what's going to end up happening is you're not going to get any real, you're going to get two imaginary solutions. Now, these are all complex solutions, right? Because a complex number is both the real and the imaginary, and any infinite possibility of either real or either imaginary, so it could be pure or real. But the idea here is, even though we didn't find any real solutions here, there are still a complex solution to our equation here. Now, just as a reminder, a real number of the form a plus bi is a complex number, right? It can have a real and an imaginary part. It could be both. A and b could be 0, so we can have a pure real or a pure imaginary. Now, with these complex numbers in the previous lesson, remember, we can add, subtract, multiply, and divide. Now, we can actually use these complex roots to create our polynomial. So we're used to doing it with just the real, right? X minus my 0. So x minus 5, x minus my 0, x minus negative 4. And I could create my polynomial doing that. You can do the same thing with your complex roots. X minus 4 minus 2i, and x minus 4 plus 2i. And so it would be written like that, and it looks like that. And that's essentially the heart of this lesson, is being able to write a polynomial using complex roots, which include imaginary numbers. Now, the non-real and irrational zeros theorem essentially states that for every complex number a plus bi in a polynomial function, if we know that it's a 0, the conjugate will also be a 0. So they always come in these conjugate pairs. We'll have a plus bi and a minus bi. And the same actually goes for irrational zeros too. If I have 3 minus root 5, I will also have 3 plus root 5. It'll always happen. We assume that it's going to exist. Now, what does that mean? In this example here, if I say create a polynomial, right, this is where I say x minus my 0, x minus my 0, dot, dot, dot. We're going through and we're creating our polynomial. We practiced last week when we multiply conjugate, last week when we multiply conjugates, right, the i's cancel out. But we need to make sure, are all my zeros present? Well, this is a plus bi, this is a minus bi. Okay, well, the complex zeros are present, we're good. So I can say x minus my 0, x minus my 0. Now from there, you just need to multiply it out. So distribute that, and so I get x minus 1 minus I, and then x minus 1 plus I. Now, I know we haven't really multiplied. If this grid helps, we haven't multiplied, when there's 3 terms. You put all the values times x is x squared, right? So you can go through and do that. I just distribute each term with every term here. So x times x is x squared, x times negative 1 is negative x times I is xi, negative 1 times x is negative x, negative 1 times negative 1 is positive 1. Notice I'm lining them up. and then negative 1 times I is negative I. And then negative I times x is negative xi. Negative 1 I times negative 1 is positive I. And negative I times I is negative I squared. Now, what's going to happen is your i's, because they are conjugates of each other, right? Last week we said when we multiply conjugate, imaginary conjugates, they cancel out. What's going to happen is your i's are going to disappear. Well, I squared is negative 1. And so that's going to be my answer. Now, you know you did this, right? Because the i's disappeared. They will always disappear when you multiply conjugates together. Now, notice on B, I only wrote 1, 0. Well, this is going to happen. We have to assume that the conjugate also exists. So even though it's not explicitly written, it's implicitly there. You have to essentially include it. So write in my 0, so x minus my 0, x minus my 0, and then multiply that out. If you need to use the grid, right, you distribute the negative. If you need to use a grid to help you multiply that out, do that. Now, just a couple of things that I wanted to point out in these practices and writing it out. Notice that the complex conjugates will always be in this form. I switched it here. You need to rewrite this. Now you can include the conjugate, right? The conjugate of that is not 2i plus 1, so we need to be careful of that. The next here is I also need to include the 2 plus I, so I have x minus my first 0, x minus my second 0, and then I still have 5, so x minus my third 0. Now a hint here is to multiply those first, because if you do that, what's going to happen is your imaginary numbers will cancel out, so then it makes it easier to multiply that through. What did we learn today? We talked about how to use imaginary numbers, complex numbers, and be able to create a polynomial. Now, a complex root is in the form of a plus bi, or a minus bi, however you want to think about it, and a and b can both be 0. So you can have a pure real number and a pure imaginary number. And then the last is, do complex roots come in conjugate pairs? In the context of zeros of a polynomial, yes, you will always have a plus or minus bi, which are conjugate pairs. This does conclude our lesson. If you have any other questions, please leave them in the comments.